Okay, then let's continue. Any questions that came up on the first part during the break? Anything you want to discuss? No. Then let's now really delve into Bayesian inference and start with some foundations. The examples will follow, but we first establish the foundations so that everything has a nice and solid foundation and we don't start somewhere in the middle. So the first thing I want to talk about is the Basin paradigm in general. So what does it mean to say we are doing Bayesian inference? So what does that entail? And the second thing then is if we're doing Bayesian inference, and usually we will end up with a posterior distribution, then what can we do with it? And there are more things that you can do with it than what I discuss here, but we have to start somewhere. Postulates of frequentist inference we've seen before, and I don't want to go into that again. So now that we start with Bayesian inference, again, I want to remind you of the central postulates. So we are going to see probabilities, and usually probabilities that apply to random variables and which are hence formulated in terms of probability mass or probability density functions. And these probabilities that you can derive, for example, from a PDF by integration, as we've seen before, they refer most of the time to degrees of belief. So when we talk about prior and posterior distributions, we mean degrees of belief. When we talk about the likelihood, one can debate what we actually mean there. I think there's also not much of a real communication about this happening, but the priors and the posteriors, these are degrees of belief. This is not something that you sample. There's no population with some population parameters or anything like that. It's just uncertainty that we want to talk about, and then we want to put numbers on, so degrees of beliefs. We will see parameters, and what we will see are probability distributions over parameters. What is important there is that you don't confuse these probability distributions over parameters with any probability distribution of parameters out there in the world. The basic model of Bayesian inference is that there's one true but unknown value of a parameter, and you quantify your uncertainty with it, or humans quantify their uncertainty about that with probability distributions, but it's not that there's a distribution of parameters in the world or something like that. That's all confusing if we start. And yes, we will use probabilistic statements about parameters with the help of probability distributions. And that's what we're going to do. So this is the first definition, and most of the definitions and stuff will be shorter, but we have to start somewhere. And I start and like to start with probabilistic models. So this P, Y, theta here, P, Y, theta, that's what I will always refer to as a probabilistic model. So what is this? A probabilistic model is a joint distribution, and typos kick in, of a family of directly observable random entities, commonly modeling data, and a family of not directly observable random entities, theta, commonly modeling parameters. So if you ignore what is written here, think of Y as data and theta as parameter. We will see examples. If you think of the Gaussian, of a Gaussian model, the Gaussian has two parameters, the expectation parameter and the variance parameter. So theta would be a two-dimensional vector here. So there would be theta 1 and theta 2. Theta 1 would be the expectation parameter, theta 2 the variance parameter. If you think of Bernoulli, we will see them later on, then there's only one. These kind of probabilistic models, so joint distributions over data and parameters, so that's the the easiest to think about it at this point, are sometimes called generative models. I don't like that term too much because it's often used and sometimes a little bit unclear what that means. Important thing is we have two kind of entities here in our model, and this whole thing is a model, right? So this has nothing to do with the real world. Data, that is Y here, that's not data on your computer. It's a model of data, and it's a probabilistic model of data, and allows for data to take on values in a probabilistic setting. Now I forgot the beginning of my sentence. And theta are the parameters. So yeah, so at this point, of course, then the question is, okay, that's a very general definition. Can we make it more concrete? And we will make it more concrete, but the principles and the foundations that we introduce here then apply all the time. This kind of joint distribution over some data and some parameters is in the Bayesian setting usually defined in terms of a marginal distribution over theta and a conditional distribution over the data given the parameter. Now, so this is where conditional probability kicks in. What we didn't discuss is that you can, of course, everything that you do with events. So in elementary probabilities, you can take two probability mass function, probability density functions to random variables. The ideas are all the same. So here we this little p always refers to a PDF or a PMF. There is a random variable, big, yeah, it's also not the nicest way to write things here, but anyway, there's a theta, it has some probability density associated with it, and there's a conditional distribution of y given theta. And this is just if you then, for example, put p theta on the other side, so divide here is again just the definition of conditional probability. Yeah, so the marginal distribution of theta, that is referred to as prior, and the conditional distribution of y given theta, if you multiply them, they form a joint distribution. So you can also always start with the joint distribution if you specify this marginal probability distribution and this conditional probability distribution, and you multiply them, you end up with a joint distribution. So instead of talking about priors and likelihoods, you could also just define a joint probability distribution, because that's what you're doing when you're defining a prior probability distribution, and so a prior and a likelihood. So as I already said, this marginal distribution over the parameters is called prior. The conditional distribution of the data given the parameter is called likelihood.
But we don't know the parameter. That's the thing. We don't know really the real parameter. So how can we say that it's y given the data given the parameter if we don't know the parameter?
Yeah, because it's a model. Because we can define whatever we want, and we can make statements about how, for example, if you think of a Gaussian, you will see that later on. There's an expectation parameter, there's a variance parameter, and of course it essentially defines the probability distribution of some data, a univariate random variable. And in frequentist setting, you will choose the parameters to be parameters and nothing else. In the Basin setting, you define them as random variables, so they attain marginal distribution, and you define the probability density of the data given the parameters, but you define that. There's nothing, this has nothing to do with statistical inference, this is pure model building. You can specify the probability of a random variable given values of other random variables just because you say so. You just do that, you are creative and you write it down. You don't need to know any parameters because, and this is also the important thing, this probability distribution over parameters, this p theta, it's just your uncertainty. It's just something that you say, that's how likely I think this value of theta is, that's how likely, or how probable I should say, otherwise it gets a little confusing, how probable this value of theta is, how probable this value is. And I'm defining that. I don't need to, because this is just my model about something that might be out there in the world, but it's nothing that for which I need information. I can, of course, that's then always the big question, where do the price come from? Of course, you can try to use something that is uninformative. So say everything is equally likely, which is not the same as uninformative. Or you have good reasons to think, because you studied the literature or something, that certain parameter values are more likely. This is also not the problem of what we're discussing here. So in terms of Bayesian inference, this is more a problem of where you use this machinery of Bayesian inference, and not so much about Bayesian inference per se, because that's Bayesian inference per se is just an application of probability theory, and yeah, you can do with that whatever you want. So prior and likelihood, we discussed often. What is the notation is not awesome here. I hope it's getting better later. So these things here, these y's and these thetas, they should be different from these y's and these thetas, because they refer to the random variables, this y and this theta here, and they refer to values of this, because these are parts of the PDF. That's not awesome, sorry for that, although you would often see it also like this. Depends on which meaning you assign to p, and if it's a probability density function, then this should be written differently. I think later on I do that, but I'll overlook that here. What is often the case in basic, like in basic frequency statistics, is that you assume that individual data points are sampled identically and independently, which in the Bayesian, because now you don't have just the likelihood, but yeah, you just don't have the marginal probability of the data, but you have the likelihood, which is just the conditional distribution of the data given the parameters. This entails that this conditional distribution of the data given the parameter factorizes into individual data points. So you have the product, which of course models independence. Here it's a conditional independence given one value, or for fixed value, let's say like this, for fixed value of theta, these values that you sample from y I are independent. We will see that. Yeah, I write here random entities because I don't want to be too specific. Of course, sometimes if you, for example, think about the general linear model, then or let's say multivariate data, then your y's are vectors. And then you don't call this a random variable, but a random vector. They can also be matrices. Your parameters are often vectors. So that's why I call this whole thing a random entity, and should use a better thing for that. Although it's also fine. It's how one does it. It doesn't matter that much. So we start, and I have, so maybe we always jump here. So we always start with a probabilistic model. So we have a joint distribution over some data and some parameters. Again, there is one true but unknown value of a parameter outside in the world. we define a probability distribution about it in conjunction with a probability distribution over data. So be aware of what that means, right? So a joint distribution, that's pretty meaningful because it says something like if the parameter is this, so you specify a probability for each combination of parameter value and data value. Yeah? So if your parameter is 1, and your data is 2, you assign to that a probability. If your parameter is 1 and your data is also 1, you assign to that a probability, and so on for all possible combinations. And of course, depending on how you do that, how this assignment process is done, you of course establish what you might call functional relationships between the parameter and the data. So if you always assign a high probability if they are the same, so for example, that if theta is 1, the probability for y being 1 is also large, but the probability for y being larger than 1 or smaller than 1 is very small. Then, of course, you assign a high probability to a function that gives you dependency, so your data is just equal to the parameter. This has then very high probability under this model. So in a joint distribution, of course, and this we will also, unfortunately, because so this joint distribution is kind of the wrapper around your model that you might want to specify more in functional terms if you're doing interesting scientific theories. It's kind of yes, the wrapper, or the way I always say it, we embed these kind of functional dependencies of some data on parameters in a probabilistic model, and yeah, that's what's happening there. But so it's important to appreciate these joint distributions. We will, if one does these first steps into Bayesian inference, one doesn't look at very interesting models. That's the same with frequentist inference. The models that you look at in undergraduate statistics are not very interesting. They are usually these linear models. So everything that falls under the GLM and similar in Bayes. Yeah, and what we already also seen here is the prior distribution. So the marginal distribution over the parameters in this joint distribution is called prior distribution, and the conditional distribution given the of the data given the parameter is called likelihood. And the main problem in Bayesian inference is to obtain the other conditional distribution that you can derive from such a joint model or joint distribution, which is the probability distribution over the parameter given the data, so p theta given y. And this then actually uses what people call Bayes theorem. So this uses again, essentially the definition of conditional probability. So here you have the joint probability, and here you have the marginal probability of the data. So you integrate out the parameter. And so you have here p y theta divided by py, which is just the definition of the conditional probability of theta given y. And in the Bayesian scenario, you write this joint distribution as the product of the prior and the likelihood. And often, and this is also how we saw Bayes theorem earlier, you then here also write the joint as p theta, so the prior times the likelihood, and then integrate out the parameter. So you have what people also call the evidence, because it refers to the probability of data under the model. So the kind of way to memorize this interpretation of Bayes' theorem is the posterior is equal to the likelihood times the prior divided by the evidence. Now you always need to think about what's actually happening there if you use this in inference. Of course, what you, and this is why I call these Y's observable random entities, or better, these Y's are the values that the observable random entity epsilon takes on. What is fixed in a given Bayesian inference scenario is the data. So you have some observation, and for this observation, you determine the probability distribution of the parameter given this observation. Now, but of course, this way, the way it's written here, it allows for any kind of observation, so that you have a general procedure to do that. As I also mentioned earlier, joint distributions and conditional distributions are essentially qualitatively the same thing. If something has a very high probability, so the way if something is looking in the joint distribution like that, it's looking exactly the same way in the conditional distribution, only the scale is different, making sure that this integrates to 1. So let's say this is 0.5, and here we had, I don't know. So we rescale this so that the probabilities or the probability densities integrate to 1. And this rescaling is done by this denominator here, the evidence. If we just want to say what is the most likely posterior value of the parameters, so this is here was the parameter, then it doesn't matter whether we normalize or not. I mean, we see it even in the unnormalized way or unnormalized setting. And this is what this refers to. The posterior is proportional to the joint. It's just multiplied by a number, which is the probability of your data point, or the probability density. So just a number, 0.25 or something like that. And if one doesn't want to describe the probability posterior density, but only the most likely posterior value of the parameter, then one doesn't even need to bother with this. And that's then so with what's in the denominator, because and this is also what you should take from the prior and the likelihood you define. Yeah, so you write it down. You say my prior is this, my likelihood is this. You don't need to compute anything or something like that. You just need to define it. Now, if you then want the posterior, you need to multiply these things for a given value of y, because of course you're interested, and you can do it for all values of y, but you can also do it for a single y that you observed. But that's just a multiplication, so it's also not something that is very computationally demanding or whatever. So or tricky or anything. So this one can do quite straightforwardly. What is usually tricky and demanding is to evaluate this normalization constant here, because that's an integral, and integrals can be hard. I mean, to find antiderivatives of complicated probability density functions can be hard. Or maybe even impossible, because certain things are not integrable of certain functions. You can't define integrals. So that's where then approximate inference kicks in, and where variational inference uses optimization essentially, and numerical inference uses stochastic simulation or numerical integration. So that's where the action is. But this, what's in the denominator, you define based on your choices, and we will see the better binomial model and the Gaussian model. I think maybe at this point we go into the example. So we will jump a little bit back and forth, but I think it's a little bit better if we immediately link that to something that is a little bit more transparent. So in the better binomial model, this probabilistic model takes a specific form, namely the prior distribution takes the form of a beta distribution, hence beta, and the likelihood takes the form of a binomial distribution, hence binomial. So we define a beta distribution, we define a binomial, which is conditional on this theta because its parameter is theta. Now, so this is one example for a probabilistic model, and in the Gaussian model, both of these of the marginal distribution and the likelihood are Gaussian distributions. Now, Gaussian you might be more familiar with. Better binomial is more the old school thing, so maybe we should at this point also rehearse a little bit what binomial and beta distributions are. So the binomial distribution is the distribution of a binomial random variable. The intuition is, let's start with that, you have two possible outcomes, 0 and 1, and on a single trial of a repeated random experiment, there is a probability of 1 minus theta or theta to for 0 or 1 to occur. Yeah, think of a coin. The coin has a probability of 1 minus theta to come up 0 and a probability of theta to come up 1. Now, that is actually, if you just have this one repeat, this is called a Bernoulli distribution. So the binomial distribution where this n is 1, that's called Bernoulli distribution. You assign a probability of 1 minus theta to an outcome of 0 and a probability of theta to an outcome of 1. Now, the binomial models the sum of the outcomes in n trials. So if you, for example, do this 10 times and you have a probability for 1 being 0.2, then if you have a very nice sample, you would obtain 1, 2, or 3 ones, and the rest of them zeros. If you sum over that, you would get, of course, 2, 1, or 3. And this distribution of summed single trials, this is what the binomial describes. So it's a probability mass function. So this refers, of course, to discrete events, namely these values of the of these sums over these zeros or ones. If you have, for example, 5, if n, so if you have 5 trials, then the possible things that can happen in these sequences that are behind that, but which are not part of the binomial picture. One, so that would be if you have 5 trials, this is a possible sequence. The binomial, so the random variable that the binomial models here, of course, takes the value 2 in this case. And these sums of zeros and ones, this is what the binomial describes. Depends on the probability for each for independent trials and for each one. So if we have, for example, 5, if the n parameter of the binomial is 5, then there are 6 possible outcomes for the sum namely all zeros, 1, 1, and 4 zeros, 2 1s, and no, that was wrong. There are 6 possible outcomes, so that would be 5 zeros, no, 5 zeros and no 1, 4 zeros and 1 1, 2 1s and 3 zeros, 3 1s and 2 zeros, 4 1s and 1 0, and 5 1s and no 0. And to all of these events, which of course differ, and it's a funky distribution because the outcome space is a part of the parameter. It's very different from a Gaussian, where the parameters have nothing to do with outcome space, but in the binomial they have. One could, of course, do it differently, but that's how this here is done. If, for example, n equals 10, then we have 11 possible outcomes. And if n is 15, we have 16 possible outcomes, always one more than the number here. And then depending on the other parameter, the theta parameter, which refers to the probability for being 1, these sums, of course, have different probabilities. So if it's very unlikely that a 1 comes up, then it's of course also very likely that the sum is 0, and it's not that likely that the sum is 5. Now, if the probability that it's 1 is 0.5, and you do 10 trials, then on average you will get, or there's quite some chance that you will get that you will see observations of 5, but also of 4 and 6, because there's variation, and it's not that likely. And this is where you then want to play roulette with. It's not that likely that you see 10 ones or 10 zeros if the probability for an individual outcome is 0.5. And similarly, if there's a higher probability for 1 than 0, then of course this shifts to higher sums. So that's the binomial. The binomial is not simple, but that's the binomial. And that's the likelihood in the beta binomial model. And the parameter in the beta binomial model is theta. So n we treat as fixed. The probability mass functions that you see here, so here you see probability mass functions, so you see a probability assigned to all the possible values that these binomial random variables can take on. The probability mass functions have this functional form. So you put in an n, so you say, okay, 10 trials, you put in a y, which is you evaluate the probability for each of these possible values that can happen. And most importantly, you put in a theta, which assigns the probability for y being 1 on a single trial. And that's how this function comes about. So this is the way this binomial coefficient. We don't have to really now work out, and this is also what we're not interested in, to go from this step of independent Bernoulli trials to binomial. We just take this as the definition. This has been worked out. This works. It's actually not that easy to go from Bernoulli trials to binomial because you need convolution, because you sum over independent random variables. So you need the convolution formula to go from Bernoulli to n. The n case, so we don't want to construct the binomial distribution. We also don't want to approximate it by a Gaussian or anything. We just take it as given. That's our model. That's what we want to model. And here is an example. Maybe let's first discuss the prior distribution. Now, the crucial parameter here, and something that we don't know about, is this theta. That's a value between 0 and 1. So we assign to it a probability distribution that extends over the interval 0 to 1. And this is the beta distribution, which has a probability density on the space 0 to 1, and depending on its parameters, assigns higher probability density to certain values. If you set the parameters to 1, 1, you assign equal probability density everywhere in this interval 0 to 1. If you assign probability parameters, 10, 5, you assign higher probability to higher values than 0.5 than lower values than 0.5. So that's the beta distribution. This has a probability density which uses the gamma function, and crucially it has these parameters alpha and beta, which are quite important when updating or when doing Bayesian inference. We will get back to that. I don't want to explain everything about this right now. I just want to link it to what we've seen in general. Now, to make this very concrete in terms of applying such a model, we think of a clinical study, a clinical study where we have a treatment, let's say corona vaccination, and we then want to see whether this new corona vaccination thing works, and we evaluate that by testing the antibody level in participants 1 week or 3 weeks after the vaccination. And if this whole mRNA stuff is bullshit and doesn't work and just gets us the Bill Gates ships, he's the second time that Bill Gates came up into this system, then we would assume that the antibodies are not there in any one of those, so anyone we test, so we only get failure outcomes. If it works all the time, which of course it does, we would see only once, but we don't know. So we don't know how effective, and nobody knew how effective mRNA vaccination was before. So hence, before we do a study, we don't know what the probability for observing a success is. And one way, or if we start from there, we could say, okay, all probabilities between 0 and 1 have the same probability. And we assign a beta distribution over theta that looks like that. Of course, we could also say, okay, this is not our first mRNA vaccination. We have not used it for corona, but we used it for something else. So actually, before we started, we think, well, they worked in the past. Our subjective uncertainty is that there is a little bit more probability that this works. So we use this as a prior. How we get to the prior, there can be many ways, but we can also just read the literature and then define it. Oops. Now, this is then our prior, and then we make an observation. And here the scenario is that we have n trials, so n participants, and we observe 18 successes. So in 18 people, their antibodies were above a certain level, and in 12 people, nothing changed. Now we want to know what is our posterior uncertainty, and there we don't know anything yet because we haven't really. We have defined. We have said, okay, now we need Bayes theory. So essentially, that's where we are at, and that's why I want to know. Now go back to. But yeah, so I hope this is a little bit anschaulich. Of course, this is a very specific scenario. It's also a very interesting scenario, and this is why, of course, like Bayes and Laplace and everyone, and it's a very foundational scenario, studied this. But of course, if you think in terms of the data that you work with, I don't know if anyone works with imaging data or something like that, there you don't have these outcomes of zeros and ones, and you sum over the zeros and ones, but you have real numbers. Sometimes you have vectors and so on, and you want to do Bayesian inference for that as well. And then the better binomial model doesn't really help you, but the general framework of Bayesian inference, of course, does. And hence, we go back to the general framework and discuss the next bit. And maybe before the break, I briefly discuss two things about Bayesian estimation, because this also came up here. You can basically do Bayesian estimation and Bayesian inference always in two modes. One being batch mode and one being recursive mode. And depending on where you work and what you want to do, you encounter one more than the other. What do I mean? If you use actually Bayesian inference for scientific inference in kind of a study setting or whatever, you usually use a batch procedure where you very similar to what we just defined, or what we just discussed. Here I've done it better. So here and now the y has a tilde. So these are no, it's not that much better. Sorry. No, yi is a random variable, and these are values of that. Anyway, so if you have the data available all at the same time, then you can, based on your data set, inform your uncertainty over the parameter and derive and compute the posterior. That's what's called batch Bayesian estimation. That would mean you essentially wait in updating your prior distribution in the scenario that I just described with the 30 participants until you have all the data from all 30 participants, and then you evaluate the posterior. So you have one prior and then one posterior. There is, and this is sometimes seen, and this is so when, for example, when we do our EEG studies in Bayesian modeling of EEG, where people do sequence learning. And also, if you think about Bayesian filtering, so if you try to update where they tried to hit this comet the other day at NASA, and this goes back to Kalman filtering, and what you do there is you update sequentially, so you don't derive a single posterior, but you always use your current posterior as a prior for the next trial. This is called recursive Bayesian estimation. The point, or the one point here, is that it comes out the same way. So if you have a data set that consists of n data points, and you start with the same prior and you look at the same data set, whether you do a batch estimation or you do a recursive estimation, it comes to the same thing. But of course, in this recursive way of doing things look a little bit different, because you start with the prior over the parameter, you assign a likelihood for the first data point, you derive the posterior for the first data point, and then you use this posterior as the prior on the next trial. That then doesn't look like a prior, because it doesn't look like a marginal likelihood, because it's also already a conditional. But you could, of course, forget that you already had these observations. So in the end, these two things are actually the same thing. They just look quite different. And I don't know, has anyone done recursive Bayesian inference? No. For us, it will also not be that interesting. So we can, if you want to just do basic Bayesian statistics, not online learning. So if you're using offline in an offline setting, then we just use one can just use batch estimation. In these online settings, which are then very close to Bayesian filtering, this looks or gets a little bit more involved. And yeah, but we don't need that then. Here we deal with batch estimation. Good. Then I would suggest we stop here and then go into further aspects of the Bayesian paradigm after the break and try to link it also with our model on the better binomial. Any questions right now?
I don't know if we're going to talk about this later anyways, but this whole framework for me just really seems to make sense if you have a good intuition about what your priors are.
I don't know. First of all, if you one thing is you always have priors, even if you're doing frequentist inference, and so the example with the coin is a good example, although we can't quite see that yet. So of course, it's always this question, priors, and in frequentism, you don't have priors, so frequentism is better. If you talk about think about frequentism and maximum likelihood estimation, and in the example of a coin, if you try to estimate the parameter of a coin, or here the binomial, after one observation, and your observation is 1, you will use the maximum likelihood estimator for the Bernoulli or binomial, and that will be the average, and that will be 1. So your estimate for the parameter is 1 if you had one observation. The Bayesian approach will basically, if you start from an uninformative prior, so from the uniform distribution, will not say 1, but for example, using the posterior expectation, will say 0.6 or something like that, which of course, in the light of the evidence that you have, is much more reasonable. If you have a single observation of this phenomena of a coin that you model with this binomial model, of course makes a lot more sense after a single observation to not say, okay, the probability here, sorry, not the probability, but the my best guess for my estimate is 1. So in terms of estimates and limited data, it just makes a lot more sense to do Bayesian inference regardless how exact your priors are. So if your priors, they will always, because your inference will always be kind of a mixture between your prior and your data observation, and in frequentists, so of course, if you apply the frequentist setting to this notion of a coin, that would you would basically deny any previous knowledge about coins. And there are then two approaches to this thing. So one thing is that you always have preconceived notions about everything. I mean, your whole brain is a prior of what the world is like. The other thing is that this is actually what then refers to as objective versus subjective base. There has been a long hunt for uninformative priors, so kind of trying to remove the prior from Bayesian inference by using priors that don't convey any information about the parameter, or that don't favor certain values of parameters. So if you think about the uniform distribution over this probability, that just says every probability has the same probability of occurring. So you try to be uninformative there. Problem is, this is not really uninformative, because if you think about squaring the probability, then certain squares would get higher probability than others. That's then where the whole Jeffreys priors come in, and you need to establish criteria what you actually mean by uninformative. There is this way. So the way I see it is, yeah, you can try to be as uninformative as you like, but you will use priors in any data analysis anyway. So if you don't, so this is goes back to also what I say about data analysis in general next week or the week after in the other course. Data analysis is always a lens. You always look at data with a certain preconceived notion. And if you use a t-test, you do that. If you use non-parametric statistics, you do that. If you use ICA, you do that. If you use a neural network, you always have your lens. And in Bayesian inference, yes, it's made very explicit that you have a prior, but that's the good thing. At least you talk about it, and if two people, two scientists or two people just, if they disagree in their prior, that's fine. But at least they know that they disagree in their prior, and that's why they get different results. If they just pretend that they are doing everything completely objectively, and then they have different results, and then it takes forever to figure out that they actually didn't look at the whole thing the same, then it's more complex. So this is why, this prior doesn't really bother me. It's somehow it's this subjective and this way of looking at data, that it's not a objective thing anyway, but it's always done through a certain lens. It's just very explicit in Bayes, but it's there everywhere. And so in any model that you use to analyze data, if you compute a mean, you somehow believe that an average of your values is a good thing because why? And then a reasonable answer is because you model your data as a random variable and you want to estimate its expectation. You can also say a mean doesn't make sense. You cannot say this is then goes into the question of, for example, if you have human data, are all humans similar or are they all different? If you believe all humans are different, then it doesn't make any sense to compute a mean. Because what do you want to do with that mean? So and this question about prior is just, from my perspective, is just very explicit here.
I guess it's very good that it's explicitly stated, and as you said, okay, it's subjective, but I find that it really gives you a way to bias the analysis in a way. So, like, I guess what I want to say is, if you don't know really anything about the parameter, you should really use an uninformative prior. And not pretend to know something, because that would kind of bias the results,
sure,
in a way, right?
Yeah, sure. I mean, this is, I completely agree. The point is, it's more a question of communication, and of course, science is communication, and it's all about if I do this and this. This is what I infer. These are my conclusions. And then somebody else can say, yes, if I assume this and this would also be my conclusions, but I assume this and this. And then I have different conclusions. And then you can at least discuss it because people explicitly said, this is what I assume. So, and this is the same as sharing code for data analysis. If you don't share that and it's not clear what you actually did, and you don't even, like in cognitive neuroscience, you don't even have the language to describe what your design matrix is, and nobody understands how you actually model the data, where's the point? Then it's completely nonsense. Then nobody. So it's just, yeah. And the kind of objective subjective thing is, actually I find it fairly objective if you say this is my prior, so here this is my beta distribution, and anybody else who uses the same beta distribution as a prior gets the same result. That's fairly objective. So
well, that's subjective selection of the prior, unless you really can base it on evidence, kind of, you know?
Yeah, this is it's very hard to get that out of people's systems, but there is something maybe that makes you then happy. This helps for until you really make the step to appreciating that life is uncertain and that everything is subjective. One thing that might help is that there's something called Empirical Base, where the idea is that you estimate the prior from the data. And if so, there you essentially you make this whole probabilistic model. What you do in empirical basis that you make this probabilistic, you parameterize this probabilistic model P y theta, which of course also has the prior in it. And you then optimize the parameters of this probabilistic model in light of data. That's empirical base, where you essentially try to estimate the prior from the data. Thing is, you always start with a model. And this model is always subjective, whether you use a frequentist model where you just write down the probability of the data, or you use a neural network where you don't use any probabilities, or you just say, I compute the mean. You always start with a model. And this is just one way to quantify the uncertainty and make precise statements, so quantitative statements about the uncertainty.
As we are already talking about differences between frequentist and Bayesian statistics, could you maybe also explain, in frequentist statistics, we don't only have the point estimate for a parameter, but we also have the standard error for all parameters we can estimate it. Could you explain how the standard error from frequentist statistics is very different from the uncertainty quantified in Bayesian statistics through the posterior, by the posterior distribution?
Yeah, so you so this is very different. So that's fine. In frequentist statistics, you always look at the distribution of data and things you derive from that. So if you have data, and then you observe and data points and compute the mean of the data points, then you look at the distribution of the means, and the standard error is the variance of these estimators, right? So standard. So I don't mean now the standard error of mean. I don't mean them that you see all the time in papers, but I mean the variance of an estimator.
Yeah,
that's
the standard error would be the square root of the variance of the estimate.
Yeah. So what I wanted to distinguish from that are the sample things. So so you have this variance of some estimate or some statistics, let's say. So you have expectation, which you're interested in from bias perspective, and you have the variance. And the variability and the uncertainty, the variability, let's say, this all stems from the variability in the data. And in Bayesian inference, it's very different, because you don't talk about estimates or statistics and their variances, but you talk about the parameters, so this mu and the sigma square and their variances and parameters. So it's really at the other end, essentially, of the probabilistic model spectrum.
Okay.
So you can so for example, if the sigma squared parameter is very large, then of course you have a lot of variance. That means also your sample means vary a lot, and this the variance is large. But of course, you can, based on that, have a posterior that was maybe first fairly somewhat uniform on the positive numbers, and then based on a lot of data where you always see this high variance indicator, you have quite a narrow posterior. So you can have, of course, very high variance in the data, but a very precise measurement of this variance parameter or Gaussian. If the data actually support this. Okay, let's have a last break for today and then continue in 15 minutes. Okay, then for the last hour today, let's, I guess, finish with the foundations. There are a couple of more terms that are sensibly introduced, and we will see them again and again. We discussed posterior distribution, and we will, of course, looking at deriving the posterior distribution for the beta binomial and for the Gaussian, and then, of course, also deriving posterior distributions if things are not as simple as in the beta binomial or the Gaussian model. We've discussed that. There are a couple of terms that come up and often used in Bayesian statistics that refer to other aspects of this probabilistic model. So always remember we have this joint distribution over data and parameters, y and theta, and we gave some names already, namely probabilistic model, prior distribution to the marginal distribution of the parameter, likelihood for the conditional distribution of the data given the parameter, and posterior distribution. There's also something called marginal likelihood. This is essentially like the prior, but it's the marginal distribution of the data, not of the parameter. So you get it from integrating out the parameter. If you have a probability density function, if you have a probability mass function, of course, I left that implicit all the time. You sum over the values of the parameter. And this marginal likelihood is, first of all, it's the thing that's in the denominator in Bayesian inference. So it's this normalization constant. And be aware that this is, if you have an observed data point, this is a number, right? So that refers to the probability density of your observed data under this model. And this might be 0.27. Or 3 or something like that. So it's nothing fancy, it's just a number. It's this normalization constant. The other thing why this is interesting is because, like in frequentist inference, the probability of the data under the model is used as a model comparison criterion. So if you ever looked at F-tests in frequentist statistics, they are, of course, likelihood ratio tests, and they work by evaluating the probability density or probability mass of some observed data under two models. And then F-test and the GLM of nested models. But this is something that humans use to compare different models. And of course, one nice feature of Bayesian inference is that model comparison is in there by means of the marginal likelihood. Can also do model comparison in frequentist statistics. That always gets shoved under the carpet, but in Bayesian inference, it's there. You use the marginal likelihood for that, and that's then also sometimes called model evidence. And if you take the logarithm of that, that's also called log model evidence. And if you are then if you like the free energy principle, then the free energy is actually an approximation of the log model evidence. But we will get to that later on. So that's this quantity. So essentially, as the as another marginal probability. If you're not happy with marginal probabilities and conditional probabilities, please join us in the winter term. We will discuss marginal probabilities and their meaning and so on in some depth at the example, or you can also look at it. You don't need to join us. You can just look at the videos from last year. Or just read it anywhere. But so there is these things are explained in other places in more depth. Sometimes, but I've rarely seen that thus far, this marginal probability of the data is also called the prior predictive distribution, because it's the probability you assign to data values, I guess based on your prior, because it goes into the probabilistic model. It also features heavily in what is known as base factor. So base factor is just looking at the ratio of marginal likelihoods, like F values essentially in frequentist statistics, looking at likelihood ratios. Here we always, of course, they're called marginal likelihoods because you have this other random entity, the parameter, which is integrated out. That's base factors. I always find evaluating the marginal likelihood much more interesting than looking at base factors, because that's where the problem is. So to basically obtain this value in the first place, if you then have it and make a ratio of that, that's nice, that's a base factor. But first you need to somehow get from your probabilistic model the marginal likelihood. Then this is more, we will not do much with it. It's just sometimes there's this rhetoric of prediction, and that you need machine learning to do prediction, and that you need neural networks to do prediction, and whatever. You can do prediction with frequentist statistics. You can do prediction with Bayesian statistics. In Bayesian statistics, you can, in a way, distinguish between a prior predictive distribution, which is just the probability of the data under your probabilistic model after integrating out the parameter. But you can, of course, also, once you have observed some data, ask if you again specify a likelihood, which might be the same as previously. You can, instead of using the prior distribution, you can use your posterior distribution to form a probabilistic model, which is then conditional on your observed data. And then you can make predictions about new data based on observed data. This is very similar to actually this recursive estimation, where your prior is actually already informed by some data. Just to point out that prediction and predicting treatment outcome or making personalized medicine or whatever doesn't mean you need to use multivariate classification or something like this. This is always, it's a really predictive analytics and so on. This is always linked to, which is also weird, that it's linked to often machine learning approaches that don't use probabilities, because if you're making predictions, I think that's where you really want to know how uncertain you are. I mean, if somebody says, I think the world works like that or not, then you can say, how certain are you? I don't know. And then it doesn't really matter. But if you're making predictions about something in the future, and you need to, of course, base decision on that, then of course uncertainty quantification makes a lot of sense. So these kind of parts of a probabilistic model make a lot of sense in prediction. And I don't understand this whole prediction business that is always so linked to machine learning. So probability-free machine learning. So this is a summary. I didn't include the posterior predictive distribution in there. So just completing it with the marginal likelihood. So that's so these are the core probability distributions in a Bayesian inference setting. And so Bayesian inference, in essence, means deriving the posterior distribution, so this conditional distribution, in such a joint model that you specify in terms of a prior and likelihood. The question is then, okay, you now have this posterior distribution. What do you do with it? So the similar entity actually in frequentist statistics would be a point estimate, right? So in frequentist statistics using maximum likelihood, you can determine a maximum likelihood estimator, for example, in the t-test scenario, or the IID Gaussian with unknown expectation parameter and unknown variance parameter. There you make a best guess for your parameter. You have a maximum likelihood estimator, and that's then your best guess, and that's about it. Here you get a distribution over parameter, which is of course your posterior quantification of uncertainty. In both cases, you need to somehow then, or you can ask, okay, that's awesome, but what do I do with it? And in frequentist statistics, you usually then, you essentially always, you can choose whether you want to look at confidence intervals, or you do hypothesis testing with that, or you are happy with the estimate, which is also perfectly fine. And in Bayesian inference, you then have the posterior, and then you can ask, what do I want to do with that? And this is what I here refer to as inference summaries. This will now basically result in two things only, namely point estimates, because of course in frequentism you end up with a point estimate. You say, okay, my unknown population parameter I estimated to be 2.2, and here right now we have a probability distribution over some quantity, but maybe we also want to do something, something like our best estimate given the available evidence is 3 or something like that. So point estimates are one form of inference summary, and credible intervals, which are just the probabilities for the parameters to take on values in certain in specific intervals. One can also do Bayesian hypothesis testing. So I don't discuss that at all. You can, of course, if you think about hypothesis testing in the frequentist world, where you have null hypothesis, alternative hypothesis, you can, of course, assign a probability to your to your null hypothesis and your alternative hypothesis, and then do Bayesian hypothesis testing. This all exists. You might know, because a reproducible crisis came up, you might have heard or have seen this article, Why Most Research Findings or Medicine Research Findings Are False, by his name, Ioannidis. That's actually an example of a Bayesian hypothesis testing scenario. So that's a very influential paper in terms of reproducibility, because it basically says everything, the whole literature is false. This argument works in his, so the paper is not very good. It doesn't explain the model very well. And it only works because, so that he gets to posterior probabilities for hypothesis being true, that is very low, because he claims that there are many hypotheses, and that they are true is very unlikely. And I think that's quite unfair. So because that essentially means that all the scientists are stupid. They come up with hypotheses that where they have no good reason, or where they don't have proper prior belief. But often, of course, hypotheses are derived based on literature review and prior experience and experiments. And so to say that the alternative hypothesis that scientists come up with are very unlikely. It's a little bit condescending, but nevertheless,
how unlikely? What was his estimate? 0.1, 0.2?
Oh, I don't know.
No.
You have to look into the paper. So it also, yeah, it's a little bit of a stupid paper, but it had a big influence because it also makes this weird link to power. It's a different. So I first I thought I bring this here. So posterior predictive value is the keyword, that PPV. I thought I include this here, but that would then also take hours. So no Bayesian hypothesis testing. Just be aware that this exists, and sometimes it sneaks in places where you don't expect it. We focus on deriving point estimates and discuss what credible intervals are, sorry, not credibility intervals. Bayesian point estimation starts from the posterior distribution. But of course, sometimes you want to then also have a concrete number, not only so a posterior distribution. I don't bring a slide now, but if you have our better thing, we had, let's say, we started with a uniform, better binomial model. We started with that, and then we make some observation, maybe even this observation, and then we end up with something that has a because there are only two ones, it favors a little bit values of theta that are smaller than 0.5, but that's then where we end up in Bayesian inference, and maybe then we want to say something more, because we can of course show this to people and say this is now our posterior uncertainty, but then they say, yeah, but if you really want to, if you really would have to say a number now, what do you think is the value of this parameter? Then of course you can say different things. But if you have to say a value, then of course, yeah, you need to somehow collapse this probability distribution over this parameter to number, if they want a number. If they want a number, they get a number. The way this is addressed in Bayesian inference and which number you choose, because you can of course choose many values. So you can choose this value, which has quite low probability density. So what are the reasons for choosing this? I don't know. You can choose the one that has the highest probability density. Let's say that's here. That's the nut estimate. Or you can choose the expected value, which only for a Gaussian corresponds to some parameter. So for better distribution, you need to divide one parameter by the sum of the other parameters. We will see that again. So you can use the expected value, so the posterior expectation, that's also what's called. And the question is, why are you using one or the other? And this is then, I think, the only part where we see some decision theoretic aspects here. So we're now thinking, so the problem is now we have a posterior distribution, but somebody wants a number. And maybe an interval, but they are not happy with just looking at the posterior distribution. So then to come up with a number and deciding which number to take, it makes sense to consider what's actually happening and what happens if we choose a point estimate. So here, the formulation is in terms of a loss function. So the theta hat that you see here is the number that we report, so the point estimate, and the theta is the true but unknown value. And over the values of the true but unknown values, all the possible values, we now have a posterior distribution. So we have this p theta given y. And then we can, of course, ask, okay, if this is our setting, and we now want to figure out what kind of estimate to report. Let's quantify that, and let's take the average of our loss, which just quantifies how undesirable it is to choose a certain value theta hat if the true but unknown parameter is theta. So if theta hat could, for example, be 3 and theta could be 2, then the loss could be, okay, there's a difference of 1. So that would be, actually, this is almost a loss function that one also uses, but that doesn't come up here. A more common loss function, or one loss function that comes up here, is the squared loss function, that we take this difference, but we square it. One thing is that, of course, then deviations between our point estimate and the true but unknown value in either direction are valued equally bad. What the squaring, of course, also does is that it punishes large deviations a lot stronger than small deviations. So it says if it's a small deviation, that's okay. But if we, if you think about the square function, if we deviate more from 0, this goes up quite a lot and does not go up linearly. So, of course, the square function looks like that. If these are our deviations here between the thing that we report and the true but unknown value, then if we are here, the squared loss function gives quite some punishment, and linear loss function gets less punishment there, but already quite some punishment there. So that's this squared loss function. That's one example. Of course, one can have other loss functions. The other example that we use here is a 0-1 loss function. So we don't really need to talk about how this works, but so in terms of the math, it's fairly simple. It's if they are the same. So if the true but unknown value is 2 and you estimate it by 2, your loss is 0. Otherwise, if the true but unknown value is, for example, 3, and you estimate it by 4, then your loss is 1. So you have a loss function that's only 0 if you do that correctly. Now, the idea in Bayes estimation is to look at this loss function, which of course quantifies all the all possible combinations of your point estimate and the true but unknown parameter, and to take that point estimate, which minimizes essentially this loss function in light of the posterior distribution of your parameter. So you, for each true but unknown value, you have in your posterior, of course, a probability or probability density. So you can say the probability given the data that the true but unknown parameter is, here, let's look at another example, that it's 0.8 is quite low, and it's quite high, that it's 0.2. So you have all of this. And then you can ask for each value of theta, and each report that you make, for which you quantify how much you call it a loss. If you don't estimate this correctly, you can weigh this by the probability that your posterior parameter is actually theta. So that's what's happening in this integral here. So you weigh the true but unknown parameters by their posterior probability. Then you will get what is called the expected posterior loss for each of your possible estimates. And then you take that estimate that minimizes the posterior loss. Yeah. So you start with a loss function. So you quantify how bad do I think it is that I use this estimator if this is the true but unknown value. Then you say, okay, I now, given the data, I have a probability distribution over the true but unknown value. Now let's weigh my loss function by by this posterior and integrate out the true but unknown parameter. And then I have an expected loss for using this. You can also think about this in a frequentist way, even that helps, but you have the loss that you would have on average if you do that many times given this posterior, and then you choose that estimate that minimizes this expected posterior loss. And these kind of estimators are called base estimators. So base estimators are point estimates, in the end numbers, that you get from minimizing the expected posterior loss. The question is then, of course, and what is now a base estimator? That depends, of course, on the loss function. So if you we have if we have so it depends what actually the base estimator is, depends on the loss function. If we use the quadratic loss function, then the base estimator is the posterior expected value of the parameter. If we use the 0,1 loss function, then the base estimator is the posterior mode. Why that is, that's proven here. I don't think, given the time and so on, we want to go over that. It's actually not that hard. It requires some minimization, analytical minimization of the respective integral. But the bottom line is, if you use depending on your loss function, different aspects of your posterior distributions may be the base estimator. So the base estimator is a general concept. For a given loss function, it then might be either the expected value, which for posterior is Gaussian, then the expected value and the posterior mode are always the same thing, so that's a little boring. But if we have a beta distribution, the expected value of the beta distribution and the and the mode or the maximum or posterior value are not the same thing. And that means if you summarize your probability distribution either using the posterior expectation or the map or even the median, then what you're actually doing is using different loss functions, so having a different way to say how bad your decision is. And your decision here is the estimate. Yeah. So what does that all mean, or what? So very pragmatically, you have a posterior, and then you can basically think what you would like to do. You can, if somebody wants a number, you can say, okay, I give you the number that has the highest probability density, and then you know, okay, I'm using a 0,1 loss function here, and I'm giving you the base estimator with the 0,1 loss function, or you give them the posterior expected value. If you have a Gaussian posterior, it doesn't matter. And there are many more options. So you can, of course, think of many more loss functions and derive all sorts of different base estimators. Yeah. Yeah, sure, always.
I think I haven't understood the loss function well. If I'm the only one, and then answer quickly, of course. But what I understood is that you quantify the difference between the estimated parameter and the true parameter, but we don't know the true parameter. So how can we quantify the difference? Have you understood that?
Yeah, it's a really good question. The thing is that for so in terms of the true but unknown parameter, we consider all possible values that we allow it to take. So these are the real numbers, and so we don't need to know it. We just essentially need to define the range that it might take. So, for example, if our parameter of interest is the expected value of a Gaussian, then it's all the real numbers. Or if it's the variance of a Gaussian, then it's all the non-negative, all the positive real numbers. So this is what we need to define, but then we just define this two-variate function where we have our bivariate function where we have all possible values of the two random values, and we have all possible point estimates. And then for each combination of those, we define our loss. And if it's, we can, of course, in terms of if things are univariate, then we can also just look at the deviation between this and this. So this is what I drew there. So if they are identical, so if we're here on the diagonal, then of course the deviation is 0. And if we go away from the diagonal, then the deviation gets larger. And for each of these combinations, we assign loss. So we define it. So it might be 0, 1. If it's 0, 1 loss, then the line here is values of 0, and everything here values of 1. So it's a bivariate function. So this is now the.
But where does the line come from?
This?
Yeah.
No, that's this is just here. I mean, this is what this is supposed to be. This is R, this is R, and this is 1, and this is 1.
Yeah.
And there they are just identical.
Okay. Okay.
And this is, I just drew this line here to indicate where they are identical.
Okay.
But it's not, yeah. And if they are identical, which is of course good, so the true random value is 2, and you estimate by 2, that's good. Then the difference is 0, and then you can weigh this difference differently in terms of the loss function. But you define this loss function. You say, I want to punish large deviations.
Okay. So just say it looks like this, and then it is, that's the loss function.
Yeah, you define it. It's like it's essentially the same thing as a utility function. You for an action, so you can view this is how the analysis is. You can, of course, and how we did it in this. This is from my experience paper. You can, of course, view estimates as actions, and then for each state of the world, theta, and each action, you say if the state of the world is this, and I take this action, then I will incur this loss. Or, of course, you can think of loss always in both ways in terms of lots of gain. It doesn't matter. It's usually different in terms of loss. Yeah, so it's a utility function. You say for this kind of decision, in this state of the world, I think that's that and that's that. This is this thing with hypothesis testing and frequentist statistics where you don't really quantify how bad it is that you make a type 1 or type 2 error. But then by the whole setup, you say type 1 errors are worse because you first try to control type 1 errors, then you might or might not minimize type 2 errors. And this is an example in the Bayesian scenario where instead of doing this in this kind of ad hoc way, you just say, okay, this kind of error is that bad, and this kind of error is that bad, and so on. So you just define it. And then, of course, the thing is, this is here referring to the state of the world. And the nice thing then, of course, in Bayesian inference is that you have probabilities about the states of the world, because you have the posterior. Of course, they refer to your uncertainty about the states of the world. And then, of course, if you have for a certain action, you have so for, let's say there's a certain state of the world, and for this action you get a lot of loss. Then taking this action, if this is really the state of the world, is really bad and you don't want to take it. But if you think this is actually not the state of the world, then taking this action is not that bad. So that's the logic there.
Thank you. And what does 0-1 loss function mean then again?
No, that just means that your loss is only 0 if you if in this case the estimate is equal to the true but unknown value. So and otherwise you always incur loss. So this of course means that you want to be very precise when you estimate, but then also it doesn't matter whether you are a little bit off or you completely
that doesn't matter.
That doesn't matter.
Oh, that's
in the 0-1 loss, but it's in the squared loss it matters.
okay.
And absolute loss it also matters. So that's
So that was what you drew there. That was that the cost is linear and not.
Yeah. That is not. Yeah.
So
Sorry,
it
that's
does
not
matter how much off you are, but only
linearly. Yeah.
Okay.
Yeah, but then actually the linear loss doesn't lead to using the posterior expectation. So of course, a very intuitive thing, if you have the posterior distribution, is okay, I use the expected value of this, because that's from frequentist setting and thinking about probability always makes sense. That's what if you sample from this, which you of course don't do in Bayesian inference, but if you would think sampling from the posterior, on average, I would get this value. So the posterior expected value, of course, makes a lot of intuitive sense, but it's motivated by the squared loss function, not a linear loss function. But also a squared loss function, of course, makes more sense than a linear loss function, because a squared loss function means that if you're a little bit off, it's not that bad. But if you're far off, that's bad.
Yeah. Which one are you using?
I don't use this at all. I do frequentist inference. It depends on what. Currently, I'm not using Bayesian inference for statistical reporting for anything right now. So that's why I don't use it. No, I work on currently my research. So, or let's say, so one thing that we are doing. Oh no, it's not completely true. I was a little bit too far there. No, I'm using. What am I using in actual science? We are using maximum likelihood estimates for the PhD projects, because teaching the people Bayesian inference and teaching them proper computational modeling would take 6 years, not 3 years. And so that's why we use maximum likelihood there. And in other words, using this is the stuff that I'm doing on random field theory. This is frequentist anyway.
Okay, so you're also using frequentist.
Yeah.
Sometimes.
Yeah. Everybody's doing that. So it's so the thing. So in principle, it would be nice to do Bayesian inference for the models that we are using, but then talk to Belinda and to have people doing maximum likelihood estimation sometimes takes a little bit. Not for clicking something together and click maximum likelihood and then maximum likelihood comes out, but for formulating a model yourself and then doing maximum likelihood estimation numerically on the likelihood function that you first have to work out and so on. That takes some time, and then usually you would have a model that is actually not of the conjugate class, but where you would have to use some form of approximate inference. And yes, one can do that, but it takes some time. But of course, if we would have simpler models, then of course Bayesian inference. If we would have kind of these more t-test-t-like models, then of course it would be not an issue to use Bayesian test. Good, maybe so then just as a last bit, this is also quite short because we should also stop. Credible intervals, they are really straightforward. It's just that you describe an interval from the posterior distribution, so you don't, you have the same problems as in confidence intervals, that you don't really know how you want to define that, but so that's your posterior distribution here, and you can say, for example, so one thing that might be interesting in terms of this treatment question is, is it more likely that it's effective, or is it more likely that it's not effective? Because that's what somebody might ask. And then you can say, okay, more likely to be effective is that theta is larger than 0.5 in the data, and not being expected is theta smaller than 0.5 in the data. And these probabilities, of course, you just get from the probability density in terms of integration. So you just take this area or this area, and that's then the probability if you have a probability density function. And that's what is called a credible interval. One can, of course, do it also do it differently in terms of saying, okay, I first give a probability, like in confidence intervals, like 95%, and then ask in which interval is my parameter given or based on the posterior distribution with a 95% probability. And if your posterior is Gaussian, then that's always kind of straightforward. So if you have a posterior distribution that's Gaussian, then it's very natural to say, okay, I put my 95% probability or my symmetric about the posterior expectation. The question is what you want to do if it's not symmetric, because you could also give an interval, of course, that is not symmetric. And here you have no symmetry. So where do you put your 95% probability? Do you put them? No, so it's confusing. So you look at the probability, and then you can, of course, assign 95% of it to different intervals. This goes a little bit into the question of how to actually assign the boundaries of confidence or credible intervals. We don't need to. I don't want to actually go deeper into that. The basic point is that you have a posterior distribution, and for each interval that your parameter can take a value on, you can give a probability, and that's something. So you can say the probability of the parameter being larger than some value larger than 0 is that and that. And of course, then you can have a long discussion of what's the difference between confidence intervals and credible intervals, but they are fundamentally different in the sense that this is talking about the probability of the parameter, and confidence intervals talk about the probability of data or intervals. So one is conditioned, so that's one essentially, so confidence intervals essentially refer to probability of data given parameter, and credible intervals to the probabilities of parameters given data. And these are not necessarily the same thing. But that would now, if we really want to go into that, we would have to remind ourselves again how confidence intervals work.
That was my question with the standard error before the last break.
Yeah, but it's the same thing. It's also derived from the confidence intervals, and the statements are derived from the sampling distribution of the data. Okay. And so you know that if you compute a confidence interval according to how you compute it, and then you sample data 100 times, that in 95%, if you have a 95% confidence interval, in 95% of the cases, the confidence interval that you computed according to your rule will cover the true but unknown parameter. That's how confidence intervals are constructed. But this probability, the probability that you have, so that it covers the true but unknown parameter, is not. That's not the random thing there, because what has the probability distribution, what is the random variable, is the data. And here it's completely the other way around. The random variable is the parameter, and the data is fixed. Of course, in these posterior distributions that we look at, this is of course always then conditioned on an observation. So because for different observations, you have of course different posterior distributions. So that was kind of trying to lay some foundations. I think the most important thing here is actually this. So it's kind of the nomenclature. And then tomorrow, the first thing that we want to do is now to actually see two examples for that. Again, the beta binomial and also how the posterior distribution is worked out. And then the Gaussian, which is uses a Gaussian distribution for the data and has a Gaussian prior on the expectation parameter. The sigma square parameter is assumed to be known in the Gaussian model. There's also something called the Gaussian gamma model, where the sigma is not supposed to be known, assumed to be known. Good. That's it for today. So we are getting ever more applied. Tomorrow, more applications. And in the end, hopefully we get to using variational inference for the GM, which is very applied. Good. Then see you tomorrow. I hope I will be here.